Welcome to the video walkthrough of this online internship program. So this is actually the seventh one, seventh online internship program. You can do it at your home, or you can do it by coming into my lab. The title of this internship is Vulnerability Analysis of Coastal Zone under Changed Climate Scenarios with the help of water cycle algorithm. Okay, so prerequisite is you must have an idea about water cycle algorithm. You just scan this QR code and it will take you to a video which, if you watch minutely, then you can have an understanding of water cycle algorithm and how it can be applied for optimization. Next is particle swarm algorithm and dynamic programming algorithm. These two are also optimization techniques. So actually this particle swarm algorithm is an example of nature-based optimization technique. Water cycle is also that. And dynamic program comes under non-linear optimization technique. Okay, so why you need the knowledge of three different optimization techniques, that I'll discuss. Now this entire study is divided into three parts. One is weightage as DV. DV means design variable. As you know that in case of any optimization problem, take the example of this simple problem, y is equal to x squared, and you want to maximize y by changing the values of x. So this x become design variable because I am changing this variable to maximize y. Now sometimes you can vary x within minus infinity to plus infinity, and you can get the value of y. And sometimes this x will be, or x can be varied in between two domains or two bounds. So for our case, let us take this as x can vary between 0 to 1 and can never take the value of 0 and never take the value of 1. Okay, correct? And also x belongs to real number, set of real numbers. That means it cannot take imaginary values. So this 0 to 1, this constraint is known as bounding. And if both sides are bounded, then it is a closely bounded problem. If any one side is bounded, then it is a open bounded problem. Okay. And this is the equation y is equal to x squared is known as objective equation. X is the design variable that we are changing and y is the objective variable that is being changed. And remember, y can be either maximized or minimized, or it can be varied to achieve a targeted value. Now, in our case, our objective function will be coastal vulnerability index, and this coastal vulnerability index has its own parameter. I'm not going into the parameters, but I will just say that this coastal vulnerability index is can be defined as MXM divided by MNYM. So this X is the value of the parameters or variables which increase coastal vulnerability, and Y is the values of the variable which decrease the coastal vulnerability. So and M subscript N and N subscript M is actually denoted as weightage of the variables, and this subscript N indicates number of beneficiary variable or the number of variables which increases coastal vulnerability. Total number of variables which increases coastal vulnerability is N, and total number of variables which decreases coastal vulnerability is M. Okay, so this is just an example. You will find, you can go to the literatures of coastal vulnerability index, and you can find what are the variables that was put into the numerator. Remember, anything that is put in the numerator is increasing the ratio or the value of the ratio, and anything that is put in the denominator is actually decreasing the ratio. Now, this ratio of variables is indicated by or referred as coastal vulnerability, and it is assumed that more the CVI, more will be the coastal vulnerability. And by coastal vulnerability we mean damage or destruction of coastal zones. Or we can, in a more scientific term, we can say if the increase in risk of the coastal zones. This risk can be monetary, this risk can be environmental, this risk can be geomorphological, any type of risk it can be. Because as we all know that risk is directly proportional to vulnerability. Right? So this index is developed in such a way that the variables which are placed in numerator increases the vulnerability. The variables which are placed in the denominator decreases the vulnerability. But you know, one thing I think all of you has noticed that not all the variables are equally significant in changing the coastal vulnerability. Some have the more power to imbibe coastal vulnerability. Some have less importance in imbibing the coastal vulnerability. I am not saying increase or decrease. Okay, some variables can increase coastal vulnerability, but the magnitude of its impact is not as high as other variables. Let us say, take the example of wind. What can I say? Wind speed, and take also the example of wind direction. More the wind speed, more erosion will happen in the coastal zones. But in case of wind direction, yes, if the wind direction is parallel to the coastal zones, it will cause erosion. But if there is no speed, it cannot cause any erosion. So wind direction is not as important as wind speed, but both of them can increase coastal vulnerability by increasing the coastal erosion. So both of them will sit in the numerator. But impact of these two parameters are different on coastal vulnerability. Okay, so this wind speed will have a greater significance compared to wind direction in imposing coastal erosion, that is coastal vulnerability. But till now, in any study, these difference of significance is not made, or is not, what can I say, it is not defined in any of the studies that was conducted based on coastal vulnerability. All of them has used both the terms, but they are ignorant about their significance of impact. Okay, so in this study, we will first try to determine or define the significance of each of the variables that is a function, or that is the independent function or independent variable of coastal vulnerability. That means I can say what? Coastal vulnerability is a function of X also, Y also. I know that X can increase the vulnerability, Y will decrease the vulnerability. That is not my issue. But my issue is I use this as X and Y, but it is actually X1 to N, and this is 1 to M. That means N number of X's are there and M number of Y's are there. Right, in this equation you understood. So not all the X's, X1 and X2 has an impact which increase the CV, coastal vulnerability. But which one has a more power or more significance to impose coastal vulnerability? That is what we want to define. That is why we want to use some mensurable values. Okay, so that is my first objective. I think you understand the objective. I want to define the significance, not the parameters. So our design variable will be M and N. And in this case, the present step will take the average value of these parameters for a certain coast. Okay, and after taking this, what we will do is we will use this as design variable. They are, both of them are design variable. We will use this as constants because X and Y will be the same. Y will be at same value for every iterations. And then what we will do is we will start to iterate M and N and check the impact on this CVI. Okay, so the objective equation for the first case will become CVI, that is coastal vulnerability index, is equals to summation of M X M divided by summation of N Y M, where X and Y can vary, and not X and Y are not varying. X N and Y M is constant. Where M and N can vary, both of them are indicating the significance term or weightage of significance, whatever way you may say. So these M and N are varying, and they are the design variable. Let it given constraint like 0 to 1, they can vary between 0 to 1, but never equal to 0 to 1. And they must be, I have not mentioned here, but they are required to be belongs to the set of real numbers. They cannot take the value of imaginary numbers. Okay, then the entire process will be invalid. Okay, so now the steps are written here. Whatever I have discussed now, the steps are written here. So at the end of the optimization, another thing you must understood that in the present case, the first case, our goal is to maximize the index because I want to know which parameter has a significance to maximize coastal vulnerability. I am not interested about minimizing the coastal vulnerability. Okay, I am more interested to see at which uh, value of the weightage the vulnerability will be maximum. So here x and y, as I have said, whenever I am mentioning x and y, actually I am mentioning the group of x's and group of y's. Okay? And whenever I am saying that group of m, that is group of x, their corresponding weightage. Whenever I am saying n, that is group of n, that means the weightage of all the y's. So we are trying to determine the value of this m and n. And at the optimal point when coastal vulnerability is maximum, we will get the value of m and n. Although both these values are constrained in between 0 to 1. Okay, so this step finishes like this. After this step, what happens? We know what is the weightage of significance for each of the parameters which are responsible to increase or decrease coastal vulnerability. Okay, but now you can say that this how we are getting the value of x's and value of y's. So these values of x's and y's can be collected for single coastal zones, or you can use multiple coastal zones. It is up to you. If you use single coastal zones, then this will be valid for that zone only. If you use the value of variables for multiple zones, then it can be, this ratio can be represented or used for multiple coasts. Okay, so let us see the next step. Now variables as dB. After we have determined m and n, or I will say m's and n's, our next step is to determine the value of variables at which coastal vulnerability will be minimum. Why? Because then we can suggest the coastal managers to maintain all these variables at this value. Okay, so now what will happen? Now all the x's and all the y's will become the design variables and they will be assigned their respective magnitudes. One magnitude or lower bound magnitude, that is minimum value that it has achieved during 5 years, 1 year, 10 years, 100 years, whatever may be the scale. But use the same time scale, don't vary the time scale. And y is also same, whatever value this y has, lower minimum value and maximum value, for a decade, for a 5-year span, for a 1-year span, that is up to you. And these aims or aims will be there, but their value has already been decided in the previous step. Straight away you will use those values in this equation. So the equation will be same. CVI, coastal vulnerability index, divided by okay, Now M and N determined in the previous step. Now we are determining the x's and y's. So these variables will be now design variables. Then again you use WCA, water cycle algorithm, to this time note down to minimize coastal vulnerability. Because I want to know at which value of these variables, these input variables of coastal vulnerability, this index is become minimum. And we will try to maintain this index at these values only. Then we can expect that coastal vulnerability will be at its minimum. Okay. Okay. So this is the step 2, variables as DB. Now go to the last step, variables under climate change as DB. Okay. So remember in the first step we have determined the values of M by or N, the weightage of significance of each variable, but it has been determined when the inter-objective function is at its maximum value. Okay, for the worst case scenario, the values of M and N were determined. So we are talking about coastal vulnerability index only. Okay. And then in the next step, what we have done that we have used the value of M and N as determined in the first step, and we have considered the x's and y's as design variables and have determined their value. Okay, and I have also used the constraint where x or y is bounded in between its lower value and higher value that it can attain in the certain coastal zone. Okay, so here also iterations are done at the second step, and the value at which coastal vulnerability is minimum, note down. First step maximum, second step minimum. Okay, so there we get the optimal ratio of all our variables, which can impose minimum coastal vulnerability. Now we are doing the same thing in the third step, but here we are inducing the impact of climate change. So what happens is we are changing the lower value and higher value according to of the x's and y's as per the estimation made for them in RCP 4.5 and RCP 8.5. As you know, IPCC now has changed its scenario. Instead of using A2, B2 or A1C, B1C, etc., now they are using RCP 4.5, RCP 8.5, etc. RCP means representative. Some say it as carbon pathway, some say it as representative compensatory pathway. Okay, so both of them are correct. But there are in total, I think, 8 to 10 scenarios where RCP 4.5, I think, indicates the environmental scenario where environment is maintained properly. Citizens are law-abiding citizens. They do not break any of the environmental law. Suddenly, due to this, number of industry has reduced. So that is the scenario recommended by IPCC for this coastal change. Okay. And similarly for 8.5, it shows a very humid temperature and hot temperature, and all other aspects are same. Here, environmental law is not maintained properly. Only industrial law is the weaker. So at that juncture, what they have done is, based on the values of the variables for RCP 4.5 and RCP 8.5, only the lower value and higher value has been changed. And then again x's and y's are considered as design variable, and CVI is minimized. Okay, and M and N are constant, that design value of design variables at the first instance. So we are not changing that M and N, but we change the lower value and higher value according to this scenario RCB 4.5 and RCB 8.5. Note down, first take RCB 4.5, change LV, HV for that, get the result, then you arrange change LV and HV as per RCB 8.5, iterate, find the optimal value of CBI and then note them down. So here in the third step methodology, what we are doing, we have already explained. This lower bound and upper bound will change according to the scenarios, and we will get a new CVI, coastal vulnerability index, after optimizing it by the WC algorithm, water cycle algorithm. Now here what they will give is at what value of the variables coastal vulnerability will be at its minimum during the or in under the changed climate scenario. Okay? Sorry. Under the changed climate scenario, what value you have to maintain for your variables to get a minimum coastal vulnerability. So that was our objective for the third methodology, third step. Okay, so we have got that also. First you do it for RCB 4.5, second you do it for RCB 8.5. Now what happened is, as you know, just using single optimization technique will not serve your purpose. It may happen that if you use another algorithm, then it can yield a better result. So we must validate any result from we receive from any algorithm, computational algorithm, with another 3 to 4 computational algorithms, because they are never same. Changing of algorithm can easily change the value of optimality. So that is why we repeat the entire step with not only WCA but also with the help of particle swarm optimization. Now this can be anything. I have used PSO, but you can use GA, you can use this glowworm, you can use mind blast, any algorithm you can use, choice. And also I have used dynamic programming, because this dynamic programming is a numerical programming, not meta-heuristic. But this one is a meta-heuristic, and also WCA is a meta-heuristic. Now you can say that why only PSO LDP? Because I have chosen a representative from meta-heuristic and representative from non-linear algorithm. Because we must validate these WCA results with the help of or by comparing the same results with another meta-heuristic and nonlinear models, such that if all the three say that yes, this is this, then we can say that this is really this, or our result is validated. And in the present case, how I have selected the best algorithm among these three, I have used best, worst, and average method. Look, this is an iterative process. So, say for example, you are using 10,000 iteration to get the optimal value of CVI and corresponding values of the parameters. So, what you do is your WCA is predicting, your this PSO is predicting, and also DP is predicting. Now, how to select which one has the best solution? So what we do is we use this method known as best, worst, and average method. Now this is a minimization problem, so the lowest is the best, highest is the worst. So we compare the lowest value as predicted by the three algorithms with each other. Then the worst value, that is the maximum value as predicted by the three algorithms with one another. And also the average of all the values that was predicted in the 10,000 iteration. So 10,000 iteration means 10,000 objective function is predicted. You average it and then compare the best as received from WCA, PSO and TP. Compare. and they'll compare the PSO, and they'll compare the DP, dynamic programming. So the algorithm which has yielded lowest value among other algorithms when compared with the best values is the winner. But he has to also win by predicting the maximum objective function, minimum to other two methods, and also the average value of the objective function, minimum to the other cases. So in this way we can know at what value of the variables the all the input variables of coastal vulnerability index must be maintained under normal scenario and under the climate change scenario which is proposed by RCP 4.5 and RCP 8.5. Okay, so in this way we select which one is the better algorithm compared to other two. Okay, so if you complete this work, you will find that within these three, one is the best, and you will also find the ratio of the parameters. Beneficiary, non-beneficiary doesn't matter, but the parameters and their demand is a more concise, precise, and clear manner. Okay, so this is the third step and final step. So you must do it to complete your internship, and also remember that in WCA the best first average, these values will not remain, but if you record them, it will remain, and then you ultimately compare. So all these things have been explained. So the algorithm which has yielded the lowest CVI, the lowest CVI among the other CVI's maximum value and the average method also. Okay, and so what we are getting for that? We are getting the values of variables of the variables of the what I can say of the parameters which are used in coastal vulnerability index. Okay, so with this I